Good morning, stat students. It's been a while, and we are back today with Chapter 6, and Chapter 6 is going to be dealing with discrete probability distributions. Of course, probability distribution is familiar to you. Discrete should be familiar to you. We're going to start off this section today by reviewing what a discrete and continuous random variables are. And then we will look at identifying discrete probability distributions, constructing probability histograms. Again, this stuff that's really you've done before. Compute and interpret the mean of a discrete random variable, and interpreting the mean of a discrete random variable, and also we'll compute the standard deviation of a discrete random variable. This lesson is going to be graphing calculator active. So if you want to pause the video and get your graphing calculator, it'll be necessary for particularly computing the standard deviation. We're not going to do that by hand here the way we did early on. We'll use our calculators for calculating standard deviation. All right, so let's roll into this and let's distinguish between discrete and continuous random variables. A random variable is a numerical measurement of the outcome from a probability experiment. So its value is determined by chance. Random variables are denoted using letters such as X. Now, a random variable is just a quantity that's measurable by numerically here. So, like a person's weight, or a person's shoe size, or a person's height. You know, those are different types of possible random variables. The number of people who visit a restaurant in a day. Those are random variables, so they have a numerical measure that makes them random. A discrete random variable has either a finite or countable number of values. This is not new. So a discrete random variable is something that is countable or finite, and that's a discrete. And then a continuous random variable has infinitely many values. It can be broken down into smaller and smaller increments, right? We can get as detailed as we want to about a person's weight. For example, a person could weigh 231 pounds and 6.285739 ounces, right? We can get as specific as we want to. If we can break it down farther and farther, then it's a continuous random variable and not a discrete random variable. So if we're looking at these examples to determine whether something is discrete or continuous, again, this is review from Chapter 1 or Chapter 2, but if we're looking at to determine if these are discrete or random, the number of light bulbs that burn out in a room of 10 light bulbs in the next year. Letter B, the number of leaves on a randomly selected oak tree. And letter C, the length of time between calls to 911. So take a second to think about these. The number of light bulbs that burn out in a room of 10 light bulbs in the next year is going to be a discrete random variable. And then also the directions up there told us to state the possible values. So if we're stating the possible values, 0, 1, 2, all the way up to 10 of the light bulbs in that room could burn out in a year. Okay, it's discrete. Letter B, the number of leaves on a randomly selected oak tree. Now, this is a large number, okay, perhaps. It could be a very large oak tree, but because it's countable, it is still a discrete random variable. Okay, so it's a countable set of things. We'll go that. Now, the length of time between 911 calls is going to be a continuous random variable with time greater than 0. So those are some examples of just differentiating, or reminders about differentiating between discrete random variables and continuous random variables. Now, as we move on, we want to identify a discrete probability distribution. A probability distribution provides the possible values of a random variable and their corresponding probabilities. A probability distribution can be in the form of a table, graph, or a mathematical formula. And just like in our previous probability distributions or probability displays, we're going to have a couple of parameters that have to be met. Here's an example. The table to the right shows the probability distribution for the random variable x, where x represents the number of movies streamed on Netflix each month. Now, it's kind of interesting that this is a monthly data here. This would be more like daily data right now under the pandemic that we're under. I don't know about you guys, but I'm wearing Netflix out under this lockdown. There's just not a whole lot more to do with all the spare time that we have at home. So anyway, this is a discrete probability distribution, and the rules for a discrete probability distribution, just like in our previous chapter, the sum of the probabilities has to equal 1. So that first characteristic, the sum of all the probabilities of x have to equal 1, and all the probabilities have to be between 0 and 1 for it to be a probability distribution. Same as the previous chapter. So if we're looking at these probabilities going backwards here, 0.06 and 0.58 is 0.64, and then 22 make 86, 96, 99, and 0.01 would give us 1. And all the probabilities are between 0 and 1, so it does meet the qualifications of being a probability distribution. What about this one? Take a second to determine if this is a probability distribution under the two qualifications that we just looked at. So in this probability distribution, or not probability distribution, have all the probabilities okay, but it looks like we are not adding up to 1. The probabilities here add up to be 0.97. So something is missing in the details, and we do not have a probability distribution. Okay. What about this one? Now, this should take a whole lot less time for us to figure out, because the probability that x equals 5 is negative. You can't have a negative probability. All probabilities have to be between 0 and 1, and so that fails to meet the qualifications of a probability distribution also. Last one here. Okay, I've got all the probabilities between 0 and 1, and when I add those probabilities up, I get a sum of 1, and so that's a yes. The sum of the probabilities is equal to 1, and they're all between 0 and 1, so we've got a good probability distribution. All right, now constructing a probability histogram, it's not likely that I would ask you to do this on a test, but I might ask you to read a probability histogram, or look at it to gather data. So a probability histogram is a histogram which the horizontal axis corresponds to the value of the random variable. The vertical axis represents the probability of that value of the random variable. So if we're looking at this probability, again, our Netflix probability, and we drew a histogram of it, it would look something like that. So the probability that x is 0 is 0.6. We can look at the vertical axis here to see the probabilities, and then the horizontal axis to see the outcomes. The probability that a person would rent one video in a month is pretty high. And so that's just a graphical way of looking at the probability distribution table. So now computing and interpreting the mean of a discrete random variable. And this is the same as it's always been, the same as it was in previous chapters. The mean of a discrete random variable is given by the formula, the mean of x, or this is the population mean, right? Mu is the population symbol. So this formula here, we have the mean of a population, the mean of a random variable x is equal to the sum of all the x's times their probabilities, where x is the value of the random variable and p of x is the probability of observing the value. All right, so this formula is not really that difficult to put into play. So let's look at the previous example of our. Well, actually, this is a new example. We changed this to renting videos from a video store. This is even less relevant to you guys than the Netflix example earlier. You may not even remember what a video store is if they were in existence in your lifetime. You used to have to go to a store to rent DVDs. You couldn't rent movies at home on your TV. But anyway, the mean probability, which represents the number of DVDs a person rents from a video store during a single visit. So the probability the person rents 0 videos is equal to 0.06. The probability they rent 1 is 0.58. The probability that they might rent 2 is 0.22. 3 would be that. 4 would be that. And only one customer out of 100 would rent 5 DVDs in a single visit. So that's what we're looking at there in those probabilities. So if we wanted to find the average, the mean of this population is going to be the summation. All right, let me write my ugly summation symbol. It's the summation of all the x's times their probabilities. So what we would do is multiply 0 times that, this times this times that, add them all together to get the probability or the average number of movies rented. Okay, so 1.49 is where we're going to end up. All right, so 0 times 0.6 plus 1 times 0.58 plus all those things, we get 1.49 as our population mean. Okay, now let's look at something related to that. So the interpretation of the mean of a discrete random variable. Suppose an experiment is repeated n independent times and the value of the random variable x is recorded. As the number of repetitions of the experiment increases, the value of the n trials will approach the population mean for that random variable. Okay? In other words, let x1 be the random variable x after the first experiment, x2 be the value of the random variable x after the second experiment, and so on. Then our, again, x bar, remembering back, x bar is a sample mean. Okay, the sample mean is the sum of all of our x values, or the sum of all the values of the experiment divided by the number of values in the experiment. That formula hasn't changed, and either has this. The difference between the x bar and mu sub x, the difference between the sample mean and the population mean, gets closer to 0 as n increases. Now this is the law of large numbers that we looked at earlier on in statistics. As we get more and more samples in our more and more as our sample size grows, then our samples mean is going to be closer and closer and closer to the population mean. Okay, now here's an example that can maybe kind of help you show this. This following data represents the number of DVDs, and we're still working with the same table that was just a few slides back, right? We're still working with this same scenario, right? DVDs rented at a video store. This is population data, and so we found that the population mean was 1.49. So the average person that walks in rents 1.49 videos, DVDs. So if we just took a sample of this, let's just say that we only looked at these values right here, these customers right here. Now, if we did that, we could do a quick average on those. That would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 17 videos rented between 1, 2, 3, 4, 5, 6, 7, 8 people. 17 divided by 8. No. 17 divided by 14. There's 14 values there. Is 1.2. So the average of those is 1.2. And if we took a larger chunk of this population, we would get, values that maybe are a little closer to the population mean. But if we take all 100 of these values and average them, and we're not going to do that by hand, the actual average is 1.49. So at 100 customers, we're already up to 1.49, which is the population mean. So this is just an example of how the more people you have in your sample size, the closer your average is going to be, your sample average is going to be to the population average. And this is just a chart that shows the averages and how the averages change as the number of trials increases. So the black dots here are our running averages. If we ran like 5 trials, then our averages are down here at 0.9. But as you get closer, like at 100, then you can see that your average is really, really getting very, very close to this population average that we're looking at here of 1.49. All right. So that's just an experiment to show the average, the law of large numbers. So computing and interpreting the mean of a discrete random variable, we want to interpret that because the mean of a random variable represents what you expect to happen in the long run. It's also called the expected value of the random variable. So the expected value. So the expected number of DVDs we would expect a person to rent is 1.49. That's the expected value in that instance. But this comes into play in financial situations like this one, for example. A term life insurance policy will pay a beneficiary a sum of money upon the death of the policyholder. These policies have premiums that must be paid annually. Suppose a life insurance company sells a $250,000 one-year term life insurance policy to a 49-year-old female for $530. According to the National Vital Statistics, Volume 47, Number 28, the probability the female will survive the year is 0.99791. Compute the expected value of this policy to the insurance company. All right, so the expected value is going to come from this. All right, so here's the company outcome. The company either makes $530, right? The company either makes $530 if the person survives. The probability that they'll survive is this. Or the company loses $249,470 if the person dies, and the probability that they die is 1 minus the probability that they survive. Okay, so if the person dies, the company loses a large chunk of money. If the person survives, the company makes $530. So they're going to, life insurance is, they're going to need to sell a lot of these policies. If they only sell one and the person dies, or if only they sell 10 and one of the persons dies, they're losing a large chunk of money, right? So their profit, if you're getting into life insurance or life insurance sales, the profit is determined on the number of policies that you sell. So the expected value of the policy is going to be the average payout, okay? So they're going to make $530 if the person survives. They're going to lose $249,470 if the person dies, and that gives an expected value of $7.50. So they count on, using these probabilities, they count on profiting $7.50 per customer if they sell a large number of these policies. Okay, so if they sell 1,000 of these policies, then they're going to make $7,500. If they sell 10,000 of them, they're going to make $75,000. So the numbers grow with the expected value, and that's why you reach an age where you can no longer buy life insurance, because it's just too big of a risk for you. For the company, they can't expect to make any money, and if they don't expect to make any money, they're not going to sell it to you. Incidentally, if any of you are interested in a career in mathematics, there's lots of money to be made as actuaries, where they just calculate risk and do risk analysis and this sort of thing, crunching numbers to determine prices of insurance policies, prices of automobile insurance, things like that is all calculated this way. So pretty interesting stuff. Final objective for this section is going to be the standard deviation. And just like last time, the formula for the standard deviation is pretty complicated. The standard deviation of population is equal to the sum of all of the deviations from the mean, squared deviations from the mean, times their probabilities. So if we were going to calculate from by hand this standard deviation of this, there's a lot of there's a lot of separate calculations to do. So you would have to find all of these values. We know the mean of the population, and you take all of the deviations from the mean, right? You square those values, you multiply it times the probability of x, and then you're going to sum all of these things up and then take the square root, and that gives you 0.8699. Okay, now we're not going to do it that way. We're going to allow our calculators to do that for us. So hold on just a second. Let me get back to this example. If y'all want to take a second to write that data down, you may have already have it written down if you have it on the slide. We're going to jump over to our graphing calculator, and we're going to go to our stat menu. So if you press the stat key, and we want to edit, all right, so you can just press number 1 or hit enter, and we want to input this data. So the value of our random variables was 0, 1, 2, 3, 4, or 5. And the probabilities that corresponded with that, if you just hit a right arrow, it'll take you to list 2, 0.06, 0.58, 0.22, 0.1, 0.03. Let me go to my error there. 2. Clear. 0.03 and 0.01. All right, so always double check your data. Make sure your data is right. 0.06, 0.58, 0.22. So I got a data value that's wrong here, which is very important that we get that right. So I'm going to arrow up and make that 0.22. All right. 0.1, 0.03, 0.01. Okay, now our data is correct. And at this point, we want to go back to our stat menu. And we want to go over to calculate, so arrow over, and we want to do our one variable statistics on this set of data. So our list is list 1. The frequency list is the same as the probability. We can expect, the value of 0 to happen about 6% of the time. So that gives us our frequency, the expected value of 0. So our frequency is going to be list 2. And you can do second and 2 there to pull up list 2, and then go down to calculate. So give you a second to catch up with this. All right, so we want to calculate that, hit enter, and it tells us this. Now, incidentally, if we wanted to look back up, we could have done this to calculate the mean earlier, right? Here's our mean, here's the sample mean, is that. And we go down a little further, we can see the standard deviation is, where are we here? I gotta get out of edit mode. .9326 is our standard deviation there. Okay, So we can find our sample standard deviation or our standard deviation that way. Let's double check that again. That's something that's not sounding right to me. 0.06, 0.58, 0.22, 0.10, 0.03, 0.01. For our values, yeah, it's all good. So our sample standard deviation there is 0.932. Okay. Oops, sorry. Yeah, this 0.869 is what I was remembering, but there's our, that's the variance, and then the standard deviation is equal to 0.9327, which is what we got, okay? The variance is the summation of the squares, and then we take the square root of it to get the standard deviation. All right, so that's it for this lesson. Again, if you need to rewind through that process of calculating the standard deviation, you're welcome to do that. And your homework's on page 305. And these will also, the due dates and things will be posted on Power School Learning, so check there for this week's lessons. Hope you guys are doing well. Missing you. Hope to see you soon. Have a great day.